In this lecture, our aim is to discuss the formation of a standing wave or a stationary wave in a transmission line. In fact, definitely you have studied a standing wave in your course on waves and oscillation. I have provided a detailed discussion on a standing wave in the playlist Waves and Oscillation of my channel. If you have not a concrete knowledge of a standing wave, you may watch my video on that playlist. And when you learn about the standing wave, then you will see that actually when two waves moving in opposite direction get superposed, then a resultant wave is formed, and that very resultant wave is called a standing wave or a stationary wave. In fact, the two waves moving in opposite directions which get superposed, and that causes the formation of a standing wave. Actually, those two waves may have equal amplitude or different amplitude. Both situations are possible. When the two superposing waves have equal amplitude, equal means equal in magnitude, then actually a pure standing wave is produced. Okay? But if the amplitudes of the superposing waves are not equal in magnitude, even then a standing wave is produced, but that is not called a pure standing wave. To how much degree the wave is a standing wave, that is actually measured in terms of a parameter which is called a standing wave ratio. And we will learn about this standing wave ratio at the end of this lecture. Okay? Now, in case of transmission line, you have discussed so many things till now. First of all, we have discussed the basic line equations, and we have seen actually in case of a transmission line, there are two waves traveling in the line. Both are in fact electromagnetic wave, and those are actually called the incident wave and the reflected wave. Incident and reflected wave move just in opposite directions. So when in a transmission line there is a superposition of the incident wave and the reflected wave, then a standing wave will be produced. Okay? So in this present lecture, our aim is to discuss that very standing wave which is produced due to the superposition of incident wave and the reflected wave traveling in a transmission line. And I hope you have definitely watched all the previous videos on this transmission line which I have provided earlier. Because if your aim is to understand the idea of formation of a standing wave in a transmission line, definitely you will need the results which we have discussed in our previous lectures. So I hope you have definitely watched. Now, let us see. The wave, when you talk about the voltage variation with the distance measured from the sending end or the generator end in case of a two parallel wire transmission line, then actually you have seen earlier in my previous videos that the voltage as a function of x, where x is the distance measured from the generator end or the sending end, that is given by b times e to the power minus gamma times x plus a e to the power gamma times x. And I have discussed earlier that this term b times e to the power minus gamma times x, this actually represents the incident wave, and a e to the power gamma x, this represents the reflected wave. And in this equation, actually this gamma is called propagation constant. What is this propagation constant? What are its basic definition and what are its important characteristics? All these things you have learned in my previous video. And you have seen that actually this propagation constant gamma is a complex quantity, and in general we define it as alpha plus j beta, where alpha, this is called attenuation constant, and what is beta? Can you say? Definitely you can say. If you have watched my previous video, I have discussed these two quantities in very detail. Beta is actually called phase constant. Okay. So if you will replace the propagation constant gamma defined by alpha plus j beta in this equation for v of x, then the expression for v of x will become b times e to the power minus alpha plus j beta times x plus a times e to the power alpha plus j beta times x. Okay. And this result may be written as b times e to the power minus alpha x times e to the power minus j beta x, and plus a e to the power alpha x plus e to the power j beta x. Okay. Now e to the power j theta, here j stands for iota, this is for imaginary, and e to the power j theta is equal to cos theta plus j sin theta. So utilizing this very formula, for this e to the power minus j beta x, you may write cos beta x plus j sin minus cos minus beta x plus j times sin minus beta x. But cos minus theta is equal to cos theta. So cos minus beta x, that will be equal to cos beta x. But sin minus beta x will be equal to minus sin beta x. So instead of e to the power minus j beta x, you may write cos beta x minus j times sin beta x. Okay. And in the similar manner, instead of this e to the power j beta x, this is actually the phase factor of the wave, we can write cos beta x plus j sin beta x. Okay. In fact, our aim is to cast this equation for v of x, which will actually represent the equation of a standing wave, in a proper form, in a convenient form. And for this, let us see the first term of both of the terms in RHS. You can see the first term here is b times e to the power minus alpha x times cos beta x, and here you can see the first term is a e to the power alpha x times cos beta x. So when you will combine these two terms, you may take cos beta x as a common factor, and when you will associate these terms containing j, then you may take j sin beta x as a common factor. So doing this algebra, now you can write v of x is equal to b times e to the power minus alpha x plus a times e to the power alpha x times cos beta x. Okay, and minus j times b times e to the power minus alpha x minus a e to the power alpha x times sin beta x. Okay. Now, as you know that the alternating voltage and current are treated like a vector. Okay. Or you can say that they are treated like a phasor. So in vector form or in phasor form, this voltage V is written as V naught times e to the power minus j phi. Here phi actually represents is phase. This is the common thing. If you have studied the concept of alternating current, then you have seen such an idea. Now again, instead of this e to the power minus j phi, you may write cos phi minus j sin phi. So v of x is given as v naught times cos phi minus j times v naught sin phi. Now let us see this equation 1 and 2. Both equations defines actually the voltage V, which is actually a complex quantity. So we can equate equation 1 and 2. But you know, when two complexes are equal, then the real part of the first complex is equal to the real part of the second complex. And similarly, the imaginary part of the first complex is equal to the imaginary part of the second complex. So, equating the real and imaginary parts of the complex quantity V of x defined in equation 1 and 2, you can see we will have V naught cos phi is equal to B times e to the power minus alpha x plus a e to the power alpha x times cosine of beta x. And when you will equate the imaginary part, you will have V naught sin phi equal to B times e to the power minus alpha x minus a e to the power alpha x times sin beta x. Okay. Now actually, when you define this V of x in this manner, that is V naught times e to the power minus j pi. Actually, you do not know what are the values of V naught and phi. So now our aim will be actually to find the values of V naught and phi in terms of the known quantities. So observing these two equations 3 and 5, we can easily find the magnitude of V naught and its phase factor phi. If your aim is to find the value of V naught, what you will do? See the form of the equation. When we will square equation 3 and 4 and simply add, you will get easily the value of V naught. So let us square equation 3 and 4 and after squaring add them. So your result will be V naught square times cos square phi plus sin square phi, and that will be equal to a square of this much. This is B times e to the power minus alpha x plus a times e to the power alpha x whole square times cos square beta x, and plus this much square. This will be B times e to the power minus alpha x minus a times e to the power alpha x whole square times sin square beta x. Okay. But you know, this cos square phi plus sin square phi is equal to 1, and therefore if you will find V naught, that will be simply the square root of the expression in RHS. Therefore you can see V naught is given as a square root of B times e to the power minus alpha x plus a times e to the power alpha x whole square times cos square beta x, and plus B times e to the power minus alpha x minus a times e to the power alpha x whole square times sin square beta x. So in this way we have obtained the value of V naught. Actually this is the equation of the standing wave produced in this transmission line. Now if your aim is to find the phase of that very wave, then phi represents the phase. So for finding the value of phi, you can see we will simply divide this equation 4 by equation 3. And when you will divide equation 4 by 3, what will be in LHS? V naught will simply cancel out, and sin phi over cos phi, that will be equal to tan phi. And in RHS, this sin beta x over cos beta x, that will be tan beta x, and the remaining factor will be this much. So tan phi equal to this much times tan beta x. So combinedly equation 5 and 6 completely determine the standing wave produced in this transmission line. Okay. Now, see this equation 5 seriously. And from this equation now, some important facts is very clear, and we will actually discuss each and every important facts hidden in this equation 5. Let us see first of all, if your aim is to know what will be the maximum value of V naught and when V naught is maximum, you can see this equation. When beta x is equal to n pi, beta x is equal to n pi, then you know cos square beta x is maximum, but this sin square beta x will be 0, where n is equal to, in fact, 0, plus minus 1, plus minus 2, and so on. You know, cos 0 is 1, cos pi is minus 1, cos 2 pi is plus 1, but sin n pi is 0. So when you will take beta x equal to n pi, this cosine square beta x will have maximum value, and V naught will have also maximum value. So the maximum value of this V naught, which is I have written by V max, that is given by this much. This second term will vanish when beta equal to n pi. So V max is equal to a square root of b times e to the power minus alpha x plus a times e to the power alpha x whole square times cos square beta x. But when you will take a square root, this will be simply equal to b times e to the power minus alpha x plus a times e to the power alpha x, because this cos square beta x will be equal to 1. So this is the maximum value of this voltage. Okay. Now in the similar manner, you can see when beta x is equal to the odd multiple of pi by 2, that is 2n plus 1 times pi by 2, then this sin square beta x will be maximum and this cos square beta x will be minimum. So in this condition, you will get the minimum value of V naught, and therefore the minimum value of V naught will be equal to what? That will be simply this much, because this first term in equation 5 will vanish, and in second term this sin square beta x will be equal to 1. Okay, when you said beta x is 2n plus 1 into pi by 2, taking n equal to 0, this will be simply pi by 2. And you know cos pi by 2 is 0, but sin pi by 2 is 1. Okay. When you will take n equal to 1 or minus 1, in fact in that condition the value of cos beta x will be again 0 and the value of sin square beta x will be 1. So V minimum is equal to this much. Okay. P minimum is equal to this much. In fact, I have shown the variation of this V naught in against of x in this figure. You can see the minimum value of this V naught is not 0. Its minimum value is non-zero when the amplitude of the incident wave and the reflected wave or the superposing waves are not equal. You know, this b times e to the power minus alpha x, this is the amplitude of incident wave, and a times e to the power alpha x, this is amplitude of the reflected wave. If both are not equal, then V minimum is not 0. But when the amplitude of both of these waves will be equal, in fact in that condition V minimum will be 0. Now you know the distance between the two successive maxima or the two successive minima, this is actually equal to half of the wavelength in this case. In case of traveling wave, the distance between two successive maxima or crest is equal to wavelength. But in case of this standing wave, the distance between the two successive maxima or two successive minima, you can see in this figure, that will be equal to lambda by 2, that is half of the wavelength. Now, you have seen that this beta x is equal to n pi for maximum value of this v, and in this condition x will be equal to n pi over beta. So by this equation you can find all the values of x where the value of v naught will be maximum. Okay, and as I have told you that this v naught is not 0 even when v naught is minimum, but this is possible only when the amplitude of the superposing waves are different. Now we can further obtain some important results from this equation number 5. See this equation. I will not turn the page regularly. You can see this equation and then you can note down in your notebook and then watch the video and then discuss. You can see, if in equation 5 you consider that A is 0 but B is not 0, then the standing wave equation will be what? This will be V naught equal to B times e to the power minus alpha x. And you can see this is exponentially decaying. This is exponentially decaying. With increase in x, this V naught will decrease exponentially. But if you consider the just opposite situation, if you take B equal to 0 but A is not equal to 0, then what will be the standing wave? Then the standing wave is V naught equal to A times e to the power alpha x. This is exponentially growing wave. This is exponentially decaying wave, and this is exponentially growing wave. There will be a growth, there will be an increase in the value of V naught. Okay? And as I have told you earlier, that if the amplitude of the incident wave and the reflected wave are equal, that is modulus of A e to the power alpha x and modulus of B times e to the power minus alpha x are equal, then what will be actually equal to V naught? You can see this equation 5. In this condition, this second term will vanish because this is equal to this, and so second term will be 0. And in first term, instead of A times e to the power alpha x, now you can write B times e to the power minus alpha x, because this is our supposition. So it is evident from this equation 5 that when you consider the amplitudes of the two superposing waves, that is the incident wave and the reflected wave, are equal, then V naught will be simply equal to 2b times e to the power minus alpha x times cos beta x. Actually, this is the equation of the standing wave in this very condition. In fact, this equation is for a standing wave which is called pure standing wave. As I have told you in the beginning of my lecture, that when the two superposing waves have equal amplitude, then the created standing wave is called pure standing wave. Okay? So this equation 10 represents the pure standing wave because it has been obtained when you have considered that the amplitude of both the incident and the reflected wave, or you can say the amplitudes of the two superposing waves are equal. Okay? Now the standing wave pattern for the two oppositely traveling waves of unequal amplitude I have shown in this figure. Here in this figure I have shown a graphical plot of amplitude in against of x. And in fact, this full line curve actually represents the variation of V, and this dotted line actually represents the variation of I. Okay? So this is the wave pattern of this standing wave. Okay? Now, as I've told you in the beginning of my lecture, that how much a wave has a standing wave character, that is measured in terms of a quantity which is called a standing wave ratio, or you can also call it in this present context voltage standing wave ratio. That is, it is either called SWR, that is standing wave ratio, or voltage standing wave ratio, VSWR. Okay? Because here in case of transmission line we talk about the standing wave where we consider the variation of voltage. Here voltage acts like a wave function. As in case of sound wave, the excess pressure acts like a wave function. In case of electromagnetic wave, the electric field vector and the magnetic field vector acts like a wave function. And as I have told you in the beginning of the lectures on this transmission line, that we will discuss this transmission line not in terms of electric and magnetic field, but in terms of the voltage and current. So here voltage behaves like a wave function. Okay? So this standing wave ratio is also called voltage standing wave ratio. And how this is defined? In fact, this standing wave ratio is defined as a ratio of the maximum amplitude of the wave divided by its minimum amplitude. It means the ratio of maximum amplitude and minimum amplitude is called a standing wave ratio. So if you denote it by the symbol small e, then this small e is equal to mod of V max divided by mod of V minimum. Or in terms of current, you may also define it, that is E equal to mod of I max divided by mod of I minimum. But as you have seen earlier the expression for voltage, when you will take modulus of V max divided by modulus of V minimum, that will be simply equal to mod of B plus A divided by mod of B minus A. Okay? And now let us take B as a common factor in both the terms in numerator and in denominator. And when you will take B as a common factor, you can see the numerator will be B times 1 plus A by B, and denominator will be B times 1 minus A by B. So now this B and B will cancel out. But can you say what is this A over B? A is actually the amplitude of the reflected wave and B is the amplitude of the incident wave. So actually this ratio A by B is called reflection coefficient, and we have discussed this reflection coefficient in very detail in our previous lecture. And so instead of A over B, you can write a small e equal to 1 plus gamma divided by 1 minus gamma, where this gamma is called reflection coefficient. So this is the relation between the standing wave ratio E and the reflection coefficient gamma. This is relation between SWR, standing wave ratio E, and the reflection coefficient gamma. Okay. Now, in terms of E, you can also express the value of gamma. And for this, let us see. If you try to find E minus E1, you have seen that this E, which is SWR, that is standing wave ratio, that is 1 plus gamma over 1 minus gamma. So this E minus 1 will be 1 plus gamma by 1 minus gamma minus 1. And when you will take the LCM, your result will be 1 plus gamma minus 1 plus gamma by 1 minus gamma. Now you can see this 1 and 1 will cancel out. So this is 2 gamma by 1 minus gamma. Now in the similar manner, let us try to find E plus 1. So this will be 1 plus gamma by 1 minus gamma plus 1. And when you will simplify it, you will get 2 divided by 1 minus gamma. Now let us divide this E minus 1 by this E plus 1. When you will divide it, you can see since 1 minus gamma over 1 minus gamma is a common factor, so they will 2 by 1 minus gamma is a common factor, so that will cancel out, only this gamma will remain. So E minus 1 over E plus 1, that will be equal to gamma. Okay? Or you can say that gamma equal to E minus 1 by E plus 1. So in this way, you can express the reflection coefficient gamma in terms of the SWRE. Okay? But now let us see what will be the value of this SWR, that is the standing wave ratio, in case of pure standing wave. When you talk about the pure standing wave, then modulus of B will be equal to modulus of A, and you can see the basic definition. When B and A will be equal, this denominator will be 0, and so E will be equal to mod of 2B, because B and A are equal, are divided by 0, and that will be infinity. So for a pure standing wave, the value of SWR is equal to infinity. In fact, the range of the value of E is this much. 1 is less or equal to E, and this is less or equal to infinity. It means the standing wave ratio is at least equal to 1, and its largest or highest value is infinity. When you say that its value is infinity, it means you are talking about a pure standing wave which has been formed by the superposition of the two waves of equal amplitude. But when you say that the value of SWR is 1, it means that wave has no characteristic of a standing wave, that is purely a progressive wave. Okay? No property of a standing wave. Okay? So in this way, we have discussed the idea of a standing wave in case of transmission line, and also discussed a very important parameter, SWR, that is standing wave ratio, which determines actually the degree of the property of a standing wave in a particular wave. Okay? And I think you have clearly understand this discussion. Okay, thank you very much.